Welcome to Polytech's vibrometry tutorial on validating complex models accurately and without contact using scanning laser Doppler vibrometry. Based on a suggestion from IMAC's focus group on non-contact dynamic testing, we have put together this tutorial on vibrometry. It's a best practices guide and shall provide the current user with guidelines of when and how to use a vibrometer. If you're new to vibrometry, you will gain an overview of how vibrometry is helpful in the design process of complex structures. We will touch on the theory of vibrometry, but the main focus will be on how to operate the equipment and how to optimize measurements for speed and accuracy. We will illustrate with several application examples. As you can see, for this tutorial, we have provided the slide page numbers and the timestamps, so feel free to jump to the section of interest. Let me introduce the speakers. My name is Jerome Eichenberger, Business Development Manager at Polytech here in the US.
Welcome also from my side. My name is Jörg Sauer. I'm working as a product manager at Polytech GmbH in Germany.
Let's get started with the tutorial. There are two types of vibrations. There's good vibrations and there are bad vibrations. Vibrations that are intended and unwanted vibrations. In the example of a turbine blade, unwanted vibrations or excessive vibrations could be catastrophic. In the case of a brake disc, we are all too familiar with the brake squeal that we hear if those vibrations are not controlled. In the case of speaker designs, we want to make sure the speaker cone moves uniformly in a piston motion rather than having deflection shapes that affect the audio quality negatively. The picture that you see on the top in the middle is the animation or a still shot of an animation of an ultrasonic transducer arrays for imaging. In that case, obviously, that's a good vibration. That's something we want to control accurately. In order to understand and control vibrations, we need an accurate model. An accurate model and accurate simulation is important and critical for the design engineer to optimize weight, efficiency, and performance of the structure. This will allow him to make designs and minimize the amount of prototyping he or she needs to do, and thus shorten the development cycles and optimize the time it takes to generate or develop a product from the start to its completion. Scanning Laser Doppler Vibrometry, or SLDV for short, is an ideal method for test verification because, first of all, there's no mass loading. So the data can be taken as fair value. There is no need to apply data correction. Also, with scanning laser vibrometer, you can measure the exact locations of the FE model, so there's no need to interpolate data. Vibrometers have a very high resolution that is independent of the field of view or the standoff distance, obviously within reason. Typically for a structure, a modal test on a structure, the excitation is broadband. That means that the energy is spread across many frequency lines, which means that especially in between resonances, the amplitudes can be very low. As you can see in the example on the right-hand side, the noise floor was below 50 picometers. And lastly, vibrometers can measure on pretty much any surface as long as there is light coming back. And with the latest vibrometry technology, there is no need for surface treatment. In order to know which vibrometer configuration to set up, we need to understand the application and the end goal. In the case of finite element model validation, like in the case of structural dynamics or also strain, typically 3D data is required. 3D data deflection shapes are then curve fitted to obtain the modal parameters. So in this case, high fidelity is critical, especially because the responses have to be very well resolved, not just on the resonances, but also in between the resonance at the anti-resonances. Another test scenario is the characterization of ultrasonic traveling waves for non-destructive testing. In these applications, typically the displacements are very low, so a high sensitivity vibrometer is required for visualizing the waves. Now, when it comes to sensitivity or resolution, that can be enhanced using averaging, but then that comes at a cost of longer measurement times. Some of our customers are using our instruments or vibrometers in general for troubleshooting. In the case of an electronic circuit board, the trouble could be that there is excessive noise, and in consumer electronic components that can cause adverse effect to the audio quality, or electronic circuit boards could be exposed to high levels of vibration, causing damage or components to fall off. So in the case of troubleshooting, it's a point and shoot approach or a simple 1D scan is usually sufficient. The data quality is not that critical as long as the signature of the disturbing behavior is evident. When it comes to performance validation, as in the case for ultrasonic cutting tools or imaging arrays or ultrasonic welding tools, the goal is to validate the amplitude and the frequency, and typically the amplitude is fairly high or noticeably high, so there's no need for a very high sensitivity vibrometer for this application. Quality control, vibrometers are used for quality control at end-of-line tests of motors, bearing pumps, and many other devices. Measurement speed is critical for throughput, so usually just one measurement location is being investigated. And last but not least, a lot of vibrometers are being used in university labs and institute for basic research. In a lot of those applications, the mechanical behavior is not known a priori, and so it's advised to have a vibrometer in the most complete configuration. How does a laser Doppler vibrometer work? It's a simple design. Inside the laser Doppler vibrometer, there is a laser source with a measurement beam that's pointed onto the vibrating object. The reflected beam is Doppler shifted and is being captured by the vibrometer, where the returned beam is then recombined with a reference beam on the photodetector, and so we get a frequency modulated interferometer signal. The relationship between the Doppler shift and the vibration velocity is very straightforward, as you can see here on the screen. The only other unknown is the wavelength of the laser tube, so the optical portion of the vibrometer is calibration free. It's a very reliable method for measuring vibrations, having a flat frequency response curve from DC up to megahertz and even gigahertz. Also, what you'll notice is that the Doppler shift in frequency is dependent on the refraction index of the medium where the laser beam is going through. So vibrometers can be used for characterizing sound fields. For example, an ultrasonic transducer in water or in air. This is called refractovibrometry. What you see here in the schematic is a heterodyne design of a vibrometer. Comes with a Bragg cell or acousto-optic modulator that shifts the baseband in frequency, which allows to detect directionality of the movement, but also make sure to achieve the lowest noise, especially at low frequencies. There are other vibrometer designs like the homodyne or self-mixing design, but it has the heterodyne principle has proven to be the most versatile and stable design for a wide range of applications. So with the frequency modulated interferometer signal that comes from the photodetector, we can then demodulate that signal and we will obtain velocity, displacement, and acceleration in real time. Those are analog signals. The real-time signal can also be extracted, in which case there is no need for any data acquisition hardware. In order to capture deflection shapes, it is necessary to measure an entire grid of points across the test object. This is being done with the Scanning Laser Doppler Vibrometer also called SLDV. In this case, the vibrometer is packaged into a scanning head that comes with steering mirrors and a camera. This allows the user to automate a test across a grid of points on a surface without having to manually reposition the laser. The scan speed is 30 points per second, so fairly fast, but the limitation of the entire measurement obviously also depends on the other setup parameters like the data acquisition parameters, the averaging, and so forth. This will be discussed in more detail in a later section of this tutorial. Excuse me. Now, it's important for scanning laser vibrometry measurements that the reference signal, there's a reference signal to establish a phase reference between the measurement points. This can be done either by capturing the drive signal or a trigger event or the force signal or a measurement or a signal from a reference sensor, which in turn could also be a vibrometer, a single point vibrometer, for example. For complex structures, typically the motion is is in all three directions. In a lot of cases, the direction of motion is not known, in which case it is recommended to using a 3D vibrometer. This consists of 3 vibrometer heads or 3 scanning heads that measure the same location, but just from different angles. Knowing the geometry and the orientation of the object as well as the sensors allows the user or the system then to extract the orthogonal velocity components in X, Y, and Z. This process we will also go into more detail in a later section. Choosing the right configuration of a vibrometer, we would like to point out 2 main considerations. So the first one will be the direction of motion. We're looking at ultrasonically driven tools for that. In this case, in the first case, we're looking at a wire bonder. We can assume that the motion goes back and forth. In this case, a single point or a 1D scanning vibrometer will be the right choice. The same with a dental scaler that goes in linear motion. We can use either a single point or a 1D scanning vibrometer. If, in this case, a dental scaler has a motion that's rotating, then we need to measure from 3 directions to be able to capture the full 3D motion of the tip of that dental scaler. In the last example, we're looking at an ultrasonic welding tool. Typically, it's not possible to measure in the vertical direction. So we need to measure the motion from the side, but the motion is in vertical direction. So we need to use either an in-plane vibrometer or a 3D sensor. Here is an overview of the different types of vibrometers. So we can measure out of plane, we can measure in plane, we can measure differentially. We can measure the rotational dynamics of a shaft, for example. Then there's the set of full field vibrometers, like scanning vibrometers, 3D scanning vibrometers, and multi-point systems. And for very small structures, the microscopic vibrometers will be most appropriate. In this case, there's also the option to measure in 1D or 3D or scanning. So looking at this palette of vibrometers, it's obvious that there's a lot of versatility to the applications that vibrometers can serve. The technology inside each of these instruments is based on the same principle as we discussed, but it's just the application that's different. Vibrometers can measure from, as I mentioned, from sub-hertz to gigahertz in frequency, measure on shiny and dark surfaces, on flat and curved surfaces, measure on large structures as well as microstructures from close up or from far away. The other consideration when choosing a vibrometer I would like to draw your attention to is the wavelength of the vibrometer itself. There are Heaney-based vibrometers using a red laser beam at 633 nanometers. It's a very simple vibrometer design and works very well in most applications. As a matter of fact, if the amount of return light is high, so on cooperative surfaces, the resolution is excellent. This is due to the fact that the phase noise of the helium neon laser tube is very low. Using visible light, allows us to measure through water. As you can see in the schematic on the right, this is a setup for measuring the sound field in water of a ultrasonic sound source. Using visible light also allows us to position the beam very accurately. A spot diameter of less than a micron can be achieved. On the other side, we have the infrared vibrometers. Now, being at a longer wavelength kind of works against us when it comes to resolution, just because the wavelength is longer. But on the other hand, more photons can be collected than with a Heaney-based vibrometer within the same laser class. So more photons means more signal to noise. This becomes evident mainly on uncooperative surfaces. So with an infrared vibrometer, surface treatment is usually not necessary. However, an infrared-based vibrometer is a little more complex. There are 2 lasers required. An additional pilot laser is needed, so in order to view the measurement location. On the right-hand side, you see an example of a measurement on a composite panel. This is a very dark surface. In the center, a piezo that emits ultrasonic energy, and then the circle in dash, the dashed circle basically indicates where the defect is at. Looking at the measurement, we see a clear interaction of the ultrasonic wave with the defect. There are a lot of applications where the infrared-based or the Heaney-based vibrometers would work, and in some cases, the Heaney-based vibrometer is chosen just because of price.
If we want to optimize the setup and test parameters, we have to look what we want to optimize. First of all, optimization of the signal-to-noise ratio is always very important and very helpful for post-processing. The parameters we can influence are the standoff distance, setting of the measurement parameters, and we look at the surface effects. The second thing we want to optimize, of course, the scan time. The test time, total test time, is key to reduce it, and choosing the right amount of measurement points is one parameter we can influence, as well as the measurement parameters again, and we look at averaging. Let's look at the signal level, which is a measure for noise. So if you look at this graph here, we see there are 2 parameters. One is the standoff distance, and the other one is the reflectivity. If we look at a diffuse white surface, a piece of paper for example, we see that the signal level is somewhere in the middle, and the further you go away, it will drop. And if we look at the retroreflective film, which has the highest reflectivity, we get full signal level, where the diffuse white surface already has a signal drop. So these are the 2 parameters we have. There's also the angle of incidence. If we have the angle of incidence as a measure, if you're perpendicular, we have the best reflectivity, the most light gets back, we get the best signal to noise ratio. If we have measuring under a certain angle, a part of the light is reflected away from the optics in our measurement direction, so we get a reduced signal level. The signal level can also vary with the speckle pattern due to lateral movement or vibration, which is something which we will explain later a little bit how this effect occurs. And please note that the accuracy of an LDV is not affected by the returned light. It's just changing the amount of noise in the signal. Let's talk about surface effects and signal to noise ratio. The angle of incidence is important, especially with curved surfaces. Part of the light is always lost if you are not perpendicular on the surface. So especially with specular surfaces, you have very quickly total reflection and no light is coming back into the sensor, meaning you have no information on the vibration. You can use mirrors to access inclined surfaces, for example, or spray the surface with a scattering material. If you look at this little graph, we show the scattering properties of surfaces. So we are incident on the surface under a certain angle, and a part of the light is scattered back into the optics, and a part of the light is reflected and scattered in other directions. So especially if you're measuring with a 3D scanning laser vibrometers, you're always measuring under an angle, so you always have a certain angle of incidence unequal to perpendicular. So here the surface properties are important. The good news is that with most engineered surfaces, surface preparation is not required. The amount of returned light which comes back into our optics is indicated by the signal level indicator, or RSSI. If you look at the noise levels, so we have three graphs here. One is for a mirror, so best reflectivity, a white surface and a black surface. You see that the noise levels are quite different. Note that the upper right one is in nanometers per second, while the other ones are in micrometers per second. So at a given surface reflectivity, the noise level depends on the laser output power and wavelength, as Jerome already pointed out. So that depends on the sensor head you've chosen, the focal length of the sensor head and the objective, the working distance, which depends on the experiment normally, and the bandwidth and the maximum velocity depend also on the experiment. Be careful, choose just the right bandwidth and the right velocity, not too high, because that also adds noise to the signal. What we haven't talked about and what is really necessary to have in mind is the influence of the surface roughness on the noise. If it comes to rough surfaces, the RSSI level is fluctuating, which is inherent with all laser Doppler vibrometers due to the coherent laser light. You can see that in the graph. So if you have a light source, the light is shining on a rough surface and the optical path length is always different from the source to the detector, and the effect, so-called speckle effect, occurs due to constructive and destructive interferences. So we get more or less light on the detector depending on the position of the surface. The effect is we get an increased noise level, so we need more time for averaging, or we need surface preparation. So the higher the reflectivity, the lower the effect. As a mitigation, there are tracking filters implemented, also so-called speckle tracking. It's a slight movement of the laser beam during the measurement. But there's also a way to solve the effect. And this is the so-called multi-channel interferometer featuring diversity reception. We call it QTAC. That's a patented technology just introduced on the market. And we use the statistic fluctuation received from multiple detectors to combine it to a stable and continuous signal. So it's a combination of optics and electronics implemented in the Vibroflex system. And the effect is a higher optical sensitivity and a better signal to noise ratio, which we'll see in the measurements. So if you switch QTAC on, the noise is dramatically lower. Now we can compare again both graphs. And with the elimination of the surface effect, the noise is gone. Now we have optimized the signal to noise ratio by different means. Now we want to optimize the measurement time, and the test time is defined by the sampling time, determined by the frequency resolution. So 1/t is the highest frequency resolution we can achieve. The number of scan points, so check with your FE model which spatial resolution is required to get the deflection shapes and the mode shapes resolved. Delete overlapping points, they just cost more time. And look at the number of averages, choose the right interferometer technology, of course. So if you have low reflectivity, take a an infrared system, check for the signal level with a test measurement and look for the coherence and choose overlap at as high as adequate. To give you a little bit more insight into that, we will show you a little video which we pre-recorded on a real test. A short introduction to the video, so simulation and reality, so we want to update a model. Reality typically is infinitely complex. Look at this tree, try to model its dynamics would be quite difficult. Simulation tries to work with finite complexity, so reduced models, assumptions for the boundary conditions, so this is how my tree looks like if it's modeled. And with the finite element method, we divide the structure into finite elements with defined boundary conditions and material parameters. But what are the appropriate parameters? And that's where we need the test for. So if you have an FEE model, as we said, we have the parameters, boundary conditions, geometry, and then we build a prototype with deviating material parameters and boundary conditions. Geometry deviations play a role. Think about casted materials, damping in joints, that's a very prominent issue. And we have, of course, the mass itself, material damping, and the support of the test structure. Mass is easy to check. Put it on your prototype on a scale and see if it correlates to the mass you have calculated in your model. Then we perform the test, the experimental modal analysis, and then we extract the parameters, the eigenfrequency, eigenvectors, modal damping, and in case of the scanning laser vibrometry, also the true geometry, because that's something we get as a return during the measurement. So we're bridging the gap between reality and the model, and then we can do a FE model validation or updating. And then the circle is closed. So some rules. So with an experimental modal analysis for model validation, we measure the multiple responses to one or more known input forces typically. The excitation must be repeatable, and especially because we can do it only with linear structures. So if your structure is not linear, you have to take care that the force level of the excitation is very consistent. Otherwise, you will get smearing in responses and you will not have a good update for your model. You have to replicate the model assumptions in the test setup, like boundary conditions. So if it's clamped, it has to be clamped. If it's free-free, it has to be free-free. Avoid mass loading and stiffening. So if you look at the equation of motion, you will influence with additional mass the mass matrix, and also typically stiffening effects occur if you glue something on the structure. But we are measuring with laser light, so we don't have this issue with scanning laser vibrometry. And remember, test results represent the reality, so you have to adjust the model typically. Now let's look at the short video. For the model validation, we use as a test case a casted cover, where we get the geometry from a FE model. We will show the actual setup of the 3D scanning laser vibrometer, define the necessary parameters, and do a quality check of the setup. We also touch the post-processing of the data in a curve fit to extract the modal parameters. So here we've got the test setup. We're using a 3D configuration with 3 scanning heads. The sample is supported in rubber strings for a free condition, and an automatic modal hammer, providing a consistent input force, crucial with nonlinear structures, is used to excite the structure. And of course we need an operator, software and some electronics. Setup starts with a so-called 2D alignment. This lets the laser follow your mouse for an easy setup. To perform the alignment, the laser is moved to several positions in the video image. A machine vision tool called high contrast laser display will recognize the position of the laser and store the scanner angles for this position. This is performed for all three heads. The three lasers now follow synchronously the mouse, which will support the next steps. Now we make the arbitrary positions of the scanning heads known to the software. This allows for a coordinate transformation of the raw data of each sensor into a common Cartesian coordinate system. The three lasers are superimposed in 4 reference points, while the distance to each point is measured using the internal distance sensor. Now the sensor coordinate system is defined and the laser will now precisely match in all points of the sample surface. In this test, the measurement grid is imported from a FE program. The results of the test are expected in the object coordinate system of the sample. Both coordinate systems will be matched in the next step. The imported grid will come with its own coordinate system. So we identify 4 points with known coordinates, for example from CID or FE, transfer them into the PSV software and confirm by marking the point with a laser. Now all vibration data will be transferred in the coordinate system of the FE model for straightforward validation and updating. Now we optimize the grid to reduce the measurement time and adapt it to the test requirements. The last alignment step made the imported grid exactly match the video image. To optimize the grid, we reject the optically hidden points at the back and the side for this test. Using a coarsening tool, we reduce the accessible part of the grid to a spatial density that allows for resolving the highest required mode shape. There is no loss of information, but a huge gain in measurement time. For a hammer excitation, the appropriate settings for windowing, decay time and repetition frequency along with bandwidth and average settings are required. We do some sample measurements at one point to test the settings and perform a subsequent quality check. Averaging for a stable signal-to-noise ratio, force window setting for the force signal, bandwidth and frequency resolution need to be adjusted to the test requirements, as well as triggering on the force signal. For good results, the driving point function is analyzed and the force signal is checked for double hits. Checking the data quality based on the driving point function is crucial before starting the scan. The phase plot is easy to interpret and must show the 180-degree phase jump. A SLDV provides the data instantaneously without post-processing, making these checks really easy. Adjustments can be judged in real time. We position the laser at the driving point opposite the hammer impact point. The FRF at the driving point is a good indicator. Resonances have to be followed by anti-resonances. The coherence should be close to 1, except for the frequency of the anti-resonances. If the settings are correct and we are satisfied with the data quality, the scan is started. The results of this well-prepared measurement are the operational deflection shapes and a set of 3D FRF at each node. In an averaged FRF over all points, we can select the resonance frequencies and check the operational deflection shapes. In our case, we find the plate-like shapes like the first bending, torsion, and so on up to high frequencies. The point density is high enough to resolve all shapes up to 10 kHz. The test is now finished and we can go into post-processing. From the test we obtained operational deflection shapes, but for validation we need to get mode shapes along with modal damping and eigenfrequencies, which we can process in curve fitting. The PSV data file containing the geometry and the FRFs is imported in the post-processing suite Polywave. The curve fitting process can be either performed in sections or of the full spectrum. This has to be decided upon the modal density and damping. The stability diagram shows the stable modes, which are automatically selected based on the convergence of the solution of the single value decomposition. Mode shapes and modal damping are calculated for each stable solution. Curve fitting is an approximation method. Depending on the input data quality, the output can vary. Checking quality indicators is thus recommended before using the data for validation purposes. The complexity is an indicator for the phase stability of a solution. A low value indicates a stable phase for all FRF at the nominal frequency. High values on the other side hint for a failed curve fitting and hint that it is not a real mode. The automag is comparing the mode shapes to themselves. The diagonal compares the same modes and the mag value has to be always 1. If the off-diagonal values, for example mode 1 and mode 5, have a value not equal to 0, this indicates that the modes are similar, which hints for a just numeric mode. The synthesized FRF is generated from the solutions for each mode. It should well fit the complex mode indicator function. In this case we fitted just the first 5 modes and the fit is really looking very well, indicating that the curve fitting process was succeeding. If all checks are okay, the extracted data can be fed back into the FE or into a model updating software to optimize the model to reliably predict the dynamics of the model structure.
So in the second application example, we're going to look at a NDT application for defect detection. Ultrasonic traveling waves are used often for non-destructive testing because they interact with the defect. This is analogous to ultrasonic imaging on the human body. Non-destructive testing is becoming more and more important, especially for composite panels, because the defect is usually not visible. In the case of health monitoring applications, it's very important to understand the ultrasonic wave and how it interacts with the defect and what the signature is. In order for illustration, we're looking though at a measurement on a thin aluminum plate. This is not a simulation, but this is a measurement with the result of a measurement with the Scanning Laser Doppler Vibrometer. We have 4,200 measurement points. The displacement resolution was below a nanometer. And as you can see here in the picture of the setup, we have a piezo exciter on the back, right here on the right-hand side. We're measuring from the front. As you can see here, there's the laser spot, the scanning laser vibrometer head, and we're scanning across this plate 4,200, measuring the response at 4,200 points. So when we compare the test results with the simulation, in this case, the quality of the data is very good and we can barely tell the difference between the simulation and the experiment. Experiment is on the left-hand side and we give credit to OnScale for the simulation. OnScale offers the first cloud engineering simulation platform combining powerful multiphysics solver technology with the limitless computational power of cloud supercomputers. Having a closer look at the hole in the center, you probably have noticed there is a small hole, and as we would expect, there's a little bit of an interaction with the hole. The ultrasonic wave is somewhat disturbed by the hole, but the disturbance is not that much. This is due to the fact that the dimension of the hole is quite a bit smaller than the wavelength. So this gives us an indication of the resolution of defect detection. The higher the frequency, the smaller of a defect we can detect. In this example, the frequency of excitation was in the order of 40 kilohertz. Now, being able to go much higher, like into the megahertz or tens or even hundreds of megahertz, allows us to measure smaller and smaller defects. Let's have a look at the measurement data. In the software, in the Polytech scanning software, you're seeing a split screen with the animation image on the top and a single time trace on the bottom. The single time trace is reflecting the response at the point where the marker is at, and as I'm moving the marker further away from the source, you can see that the arrival of the time wave moves further back in time. By hitting the play button, we can then animate this traveling wave. We can also manually move that wave back and forth and control the animation that way and do a very exact analysis of the wave itself, as well as the interaction with the hole or any the other defects that should be present. Now, this measurement has been taken in the time domain, as you can see here. When you're in the time domain, you can use the single cursor and then click and drag the area of the measurement that you'd like to animate. Now, I'm going to zoom out in the time scale, and we can see that there's a lot more going on after the first impact. Let's say if we animate from here to here, we see a response that almost looks like noise, but it is not noise. It is the back reflections that keep interfering with each other. So obviously there's a high ringing going on in this plate that can be visible, but it's important to understand this is not noise. We have to, between measurements, we have to make sure we let the plate ring down so that we get to a point where the ringing is almost back to zero. Now, the same measurement can be looked at or viewed in the frequency domain. We're looking at the average spectrum of all the measurement points now. If I highlight all the measurement points, you can kind of get an idea of the density of the grid. If I animate the structure, the image or the animation shows the response at 3 kilohertz, which is where the cursor is placed at. As I move the cursor to another frequency, we can then see the corresponding animation there. So interesting to have such a simple structure showing such a complex dynamic behavior. Also interesting to see is that the amplitude of the response in between the resonances, in this case, is about 80 picometers, and that's not even the noise floor. This is basically the anti-resonance or a anti-resonance, showing still a very clearly defined animation. Let's go back to the presentation. The combination of test and simulation is very important. On the one hand, the simulation is very powerful because it provides a time and cost-effective method to simulate thousands of scenarios to fully investigate and optimize inspection. It also allows to simulate complex scenarios to gain a deeper understanding of wave behavior. But at the same time, it's important to be able to validate the accuracy of the model or the simulation by experiment in order to have the right amount of confidence in the data prediction or the behavior of a particular structure. I'd like to illustrate that with another example. Here we have a thick aluminum plate, a traveling wave that moves across the top surface and interacts with the crack that's machined in the back surface. On the left-hand side, you see the animation, the actual experiment. On the right-hand side, you see the simulation. So using this scenario allows the designer to validate the accuracy of this particular simulation, of this particular scenario with this particular crack dimension. The design analyst can then take that simulation and vary the parameters of the crack, in this case in length and in orientation, and predict the wave crack interaction behavior for all these different scenarios.
So next application example for scanning laser vibrometry and model validation is strain measurements. The motivation for stress and strain measurements is understanding the origin of stress and strain and the distribution, because you want to increase durability, you want to predict durability of components under dynamic load. Typical applications are turbine blades, high-frequency tensile tests, high-temperature strain measurements, or measurements especially on small-sized objects if you do optical measurements. The difference is optical stress and strain measurements show you the full field information, so you can localize the maximum stress in a device or in a sample. If you look at conventional measurements with strain gauges, you always have a fixed location for the sensor, like here on a turbine blade. Strain gauges have benefits, especially if you do operational measurements, if you do validation measurements. This is not so important that they're permanently installed, and repeatability is of course good if they're once installed properly. But you have a high instrumentation effort. As you can see from the picture, the resolution has certain limits, and you always load the structure with the sensors. And the strain gauges are quite sensitive to mounting errors, so you have to be really experienced to glue it correctly, especially if you glue these very small ones. So how is the measurement done? So it's a combination of measurement and post-processing. So you do you need a 3D geometry, you need a 3D vibration vector, and you get the in-plane and the out-of-plane vibration. From that you can calculate epsilon, so the strain values, which is the elongation over the base length. Then you can calculate linear strains, and if you have the material parameters available, like the Young's modulus and the Poisson ratio, you can also calculate stresses. So let's look a little bit on the measurement data. So we start with a measurement on a, let's assume a plate or a cantilever. So we have an out-of-plane ODS, which has 7 micrometers displacement. The in-plane will be in the range of about 350 nanometers, so to have a ratio, so 1/20. Then you have 1/10 is the dimension for the linear strain, so we are in the nanometer range, and for shear strain we are in the range of some nanometers. So you can imagine that this is challenging measurement. If you really want to have a precise measurement, you need to care about noise again. And how that is done in practice and what you have to care for, that is shown in the next video. The measurement of strains and the calculation of stress by means of the material parameters Young's modulus and Poisson's ratio is essential for durability predictions and thus safety relevant. Measuring the spatial distribution of strain requires assessing the relative displacements between adjoining nodal points of the surface of a sample. Due to its very high sensitivity and its ability to measure displacement in high resolution in all spatial directions, the non-contact PCB 3D scanning vibrometer is ideally suited for comparing the simulation results with the strain and stress distributions. The typical setup comprises a 3D scanning laser vibrometer, the specimen supported in the fixture, and an exciter which allows for repeatable excitation. The measurement grid can either be imported from finite element model and then aligned with a real specimen, it can also be defined manually by measuring the 3D geometry and defining scan points. Determining the precise location of each point determines the accuracy of the strain output. A machine vision technique called video triangulation is used to exactly superimpose the 3 lasers in one point prior to the measurement. As an excitation signal, a multi-sign signal is used. Its parameters are extracted from the modes in the pre-test measurement by a macro. When the measurement grid is prepared, the excitation is started and the excitation signal from the signal generator is synchronized to the scan process. The scan process is now started. The 3 lasers synchronously scan the predefined measurement points while the excitation signal is repeated for each sample. In the PSV software, the operational deflection shapes and thus the quality of the measurement results are reviewed before going into post-processing. The Polytech strain processor reads the SLVD full field data and starts post-processing based on user-selected filter parameters. It outputs surface strains and stresses. Strain is a derivative of displacement and thus sensitive to noise. Spatial filtering and removing outliers are built-in tools to optimize the strain results. Strain processor creates user-defined signal channels in the original SVD file. Thus, the strain can be visualized in the PSV software after post-processing. Now the spatially distributed directive strains are visualized. In order to validate simulation results and optimize the simulation model, the results can be exported in universal file format.
This brings us to the conclusion of this tutorial. We have learned that scanning laser Doppler vibrometry helps to achieve a more accurate model and thus helps speed up the design process for a wide range of applications. Choosing the right vibrometer and setup parameters is critical for accurate data, as we've seen in the different examples that we displayed. Various use cases were discussed, which are by no means comprehensive, and also new applications are being developed every day. If you need assistance with a particular application, please don't hesitate to reach out to us. We have a highly trained application team that supports our customers worldwide. Along those lines, I also like to draw your attention to our education kit for teachers called PolyLab. It's a turnkey kit designed for professors and teachers, typically for undergraduate vibration classes, and it covers the basics of vibration testing and modal parameters and has instructions for hands-on experiments. It's fully contained and comes with a portable vibrometer called VibroGo. It comes with the software and the test structures. And with that, I would like to thank you for listening and for your attention in Polytech's vibrometry tutorial on validating complex models accurately and without contact using scanning laser Doppler vibrometry.